All right, welcome to lecture 13 of CS 182. Today, we're going to build on our previous discussion of recurrent neural networks and transformers and discuss how these ideas can be applied to natural language processing. Now, of course, since this is a single lecture, I won't be able to give a complete overview of all topics that pertain to deep learning and NLP. NLP is a huge application area for deep learning methods, and there's a huge body of work that applies all sorts of different deep learning models to NLP problems in all sorts of different ways. So in designing this lecture, I basically had to select one topic to focus on in NLP, and the topic that I really want to go into depth on is unsupervised pretraining, because this is, I think, one of the most important ways that deep learning has impacted NLP. And I think it also illustrates, beyond just natural language processing, one of the fundamental strengths of deep learning algorithms. So the big idea in today's lecture is often referred to as unsupervised pretraining. See, deep learning works best when we have lots of data. If you recall from our discussion at the beginning of the course, in many ways, the improvements in the performance of deep learning models have paralleled substantial increases in the scale of data sets that are available to train those models. So we often talk in this class about the importance of large models, of models with many layers and so on. But it's important to remember that accompanying this increase in the size of models has been an increase in the size of data sets. And in many cases, the data sets themselves have been just as crucial, if not more so, to the success of these methods as the innovations in architectures and training methods. So the good news in regard to NLP is that there's plenty of data of text out there. So in principle, NLP should be a really great application area for deep learning methods because deep learning methods thrive on lots of data, and we have lots and lots of text data. Just go and download all of Wikipedia, download all of Project Gutenberg, scrape Reddit, get all the newspapers, all the libraries, all the social media websites, and you will get huge amounts of text representing real human written sentences containing real meaning. So that's great. This seems to suggest that NLP is kind of the sweet spot for deep learning. But the bad news is that most of this data is not labeled. You don't have newspapers that publish all of their stories in English and French to provide you with paired translation. You don't have social media websites where people will write their review and then provide a sentiment analysis label. Sometimes you do. Sometimes you could, for example, scrape Amazon reviews and predict the number of stars. But in most cases, the data is unlabeled. And in particular, even when you can find labeled data, for example, you could imagine that you could train a question answering system by downloading, let's say, questions off of Quora and then taking the corresponding answers. In most of those cases, the labeled data will still be much, much smaller than the enormous unlabeled data sets you can procure. State-of-the-art models, the models I'll describe in this lecture, are trained on hundreds of millions or even billions of sentences. Enormous amounts of data. And they work really well for that reason. So there's thousands of times more data without labels, like valid English text in books, news, and web, versus labeled and paired data like English-French translations. So the big challenge that we're faced with, if we want to make deep learning plus NLP work really, really well, is how we can use freely available and unlabeled text data to help us apply deep learning methods to NLP. And that's basically the topic of today's lecture. So what can we do with unlabeled data? Well, what we can do with unlabeled data is we can learn representations of language. So you can't just use arbitrary newspaper articles to learn how to translate English into French. That's not going to work. But what you can do is you can learn good representations of English so that you can then more easily learn how to translate those English sentences into French sentences. For example, if you learn a representation of words where semantically similar words are close together, it'll be easier to then train a downstream task based on that representation. If you learn a representation of sentences where semantically similar sentences are close together, you could imagine training such a representation on English sentences, training it separately on French sentences, and then constructing some kind of mapping between the two. So representation learning could be done without labels, and it can serve as an excellent basis for downstream learning where that representation could actually be used for some useful task, which would be trained on much smaller amounts of labeled data. So how do we represent these representations? Well, you could imagine a kind of a spectrum, where on one end of the spectrum, you have local or non-contextual representations. So these are representations of words that are independent of how those words are used in a sentence. For instance, you might naively represent the word king and president as two different entries in the dictionary. But if you understand something about the word king and president, you might actually put them into a space where they're close together. Now, that's not by itself necessarily a really great representation. It's true that king and president are, somewhat semantically related, but if you're saying, well, this person is the president of my chess club, that use of the word president, is not so related to saying, he's the king of jazz, right? So the words are similar, but depending on the context in which they're used, they do have different shades of meaning. So on the other extreme, you could imagine global context-dependent representations. These are representations that will be computed by reading in an entire sentence or even an entire paragraph of text, and then constructing representations of the tokens in that sentence that take into account the way it is used in that particular sentence or that particular paragraph. It's a kind of bespoke representation specific to that piece of text. So on the left side of the spectrum, we would have things like word embeddings. In the middle, we might have things like sentence embeddings, and on the far right side, we would have pre-trained language models that read in entire sentences and produce representations from this. And in today's lecture, we'll actually talk about both extremes of the spectrum. We'll start off with a discussion of word embeddings, and then we will actually spend considerable time discussing pre-trained language models and how those can provide even better and even more powerful representations for NLP. All right. But let's start on the left side of the spectrum. Let's start simple. How do we represent words? So before, when we talked about RNNs and sequence-to-sequence models, we saw the one-hot representation. So the one-hot representation is a vector whose length, whose dimensionality, is equal to the number of possible words. Basically, the dimensionality of this vector is the number of entries in the dictionary. So it's quite large. And all the entries are 0 except for one entry, whose index corresponds to the index of that word in the dictionary. So you basically open up the dictionary, find the word. If you number all the words, that number, its corresponding entry in the vector is 1. Okay, that's a very simple representation. It preserves all information about what the word is, but it's not very informative about the relationship and similarity between words. So two words that are almost synonyms would look completely different in this representation, as different as any two words. So it's not great, but it's not terrible. I mean, you get the information. But this stands in contrast to things like image pixels. Like if you have pixels in an image, like a pixel by itself doesn't convey a lot of information, but pixels with similar values, similar colors, are in fact similar, right? So the pixels in the image actually mean something. And furthermore, we saw convolutional neural networks squeeze even more meaning out of the structure of images by actually considering local coherence. So a filter on a convnet looks at nearby pixels because the meaning of nearby pixels is likely to be similar. So the information contained in pixels is not much. They're not a great metric space if you just subtract two images together. If you subtract two images from one another and take the norm, that doesn't really give you a great measure of image similarity. But locally, it does mean something, whereas these one-hot vectors really mean nothing independently of the dictionary from which they were constructed. So maybe if we had a more meaningful representation of words, then learning downstream tasks would be much easier. So we're going for something fairly modest here. We just want a representation of words that is better than these one-hot vectors. Ideally, a representation where words that are similar in terms of, let's say, Euclidean distance or dot product under that representation are going to mean somewhat similar things. So how can we think about constructing this sort of word representation? Well, what we're going to be after is something like this. So these are low-dimensional projections of something called word-to-vec. Word-to-vec is a method for embedding words into vectors, so it's called word-to-vec because it turns words into vectors, such that semantically similar words are close together, and furthermore, changes in words in this latent word space actually have semantic meaning too. And we'll see what that means shortly, so if that doesn't make sense, don't worry about it. But hopefully just from looking at these pictures, you can get some rough intuitive understanding for what these word embeddings are trying to achieve. So if you look at the picture on the left, you can see in the top left corner you have pepper, salt, mix, put, flour, soft, good, oven, roll, right? So these are kind of cooking related words, and even more specific, not just cooking, but it specifically looks like baking, right? And then if you go down from there, you get your, ours, cold, pot, pan, dish, cover. So these are also food related words, but now it's sort of drifting from cooking to maybe like storing food, like, you know, your dish will get cold or something. If you go to the right, you can see words that correspond more to food items, so fat, cake, beef, veal, pork, gravy. You can see all the meat items are clustered in the top right there. So there's definite structure to this embedding. And similarly, in the snapshot on the right side of the slide, you can see, you know, at the top there's words like spacecraft, shuttle, jet powered, like fancy state-of-the-art aerospace things. If you go to the left from that, you see like aircraft, passenger, cargo, flight, airlines. So also aerospace related terms, but more related to like mundane passenger flight things. And if you go down from there, you get landing, safety, flown, fighter, heading, take, and then you get like really aggressive things like flew, blow, stay, killing, right? So maybe like the stuff at the bottom deals more with like military aviation. So as you move through the space, the kind of, you know, changes in the space correspond to semantic changes. Okay, so let's talk about how we can acquire these sorts of embeddings. So the basic idea that we're going to draw on is that the meaning of a word is to a large extent determined by what other words occur in close proximity to it. This is not an obvious statement, but if you think about it, it actually makes sense. Like the word reign is used close to like words like king and queen, and maybe to a lesser extent dictator or president. So you might surmise from that the word reign has something to do with like leaders of countries, and then you would put it closer to the leaders of countries. Put another way, the more interchangeable two words are with each other, the more similar they are. So the word reign doesn't just occur close to presidents and kings and dictators. The word rule also occurs close to presidents and kings and dictators, and the two are often interchangeable. Therefore, they should be very close together in your embedding of words. Here's another example: Seattle hotel versus Seattle motel. Right? You know, hotel and motel are two different words, but the way in which the word hotel is used is often very similar to the way motel is used, so you might expect that those words should lie close together in the embedding space. And the effect of putting them close together in the embedding space, when you then use that representation for downstream tasks, is that models will understand, without necessarily having seen it before, that some use of the word hotel could be close to synonymous with the same use of the word motel. Here's an example for the word banking. So these are three sentences that contain the word banking. Government debt problems turning into banking crisis, as happened in 2009, saying that Europe needs unified banking regulation to replace the hodgepodge of whatever. India has just given its banking system a shot in the arm. So from this, you might infer something about the word banking. And the terminology we're going to use is that the other words that occur close to the word in question, we'll refer to these as context words. And specifically, we'll say that a context word is a word that occurs within some distance of the center word in sentences. So the center word here is banking, that's the word in the center, and the context, in this case, is selected to be of length 5. So words that are within 5 words of the word banking. Very reasonable choice. The basic principle is that we'll pick a representation for each word such that its neighbors are close under this representation. All right. So can we predict the neighbors of a word from its embedding value? That's essentially the problem we'll be trying to tackle. So in this diagram, I have the center word, which is into, and it's located at some position t. And I have context words, which I'll refer to as O, and those are all words at some other t prime, such that t prime minus t, its absolute value is less than or equal to 5. So we'll take words within a window of 5. Here it's showing a window of 2, but a window of 5 is more typical. So one way we could think about similarities, we could say, well, maybe we can write down a prediction problem, and we could say, can you predict how likely is a particular word to be a context word for some center word? Why did we suddenly turn into prediction? Well, we'll see in a second that actually prediction and similarity can be viewed as very similar things. All right. So we'll use a tool that we're already familiar with from our discussion earlier in the semester, where we'll predict the context word O, each of the context words O, from the center word C by essentially doing logistic regression. So if you remember, logistic regression corresponds to a dot product and then a softmax. Now in regular logistic regression, we had a dot product between a weight vector and the input. Here we're instead going to use a dot product between the vector representation of O, denoted UO, and the vector representation of C, denoted VC. So for every word in our dictionary, we'll keep track of a different U vector and V vector. And then we'll say the probability that O is a context word for a center word C is going to be given by the softmax applied to the U vector for O, which is UO, transposed with the V vector for C, which is VC. So it's just the softmax on UO, VC. And of course, we normalize in the softmax by a sum over all possible words. So capital V here is the vocabulary. So we sum over all possible words that could occur, and their exponentiated dot product. So this is just the softmax distribution over all possible U vectors for a given VC vector for a given center word C. Okay. Now, this might seem like a slightly arbitrary choice, but you'll see in a second why this actually makes sense. Now, this looks a bit like a logistic regression model. How do we train this? Well, we'll train it exactly the way that we trained logistic regression before. Except that now, instead of our parameters being the weights for different classes, our parameters are all the U vectors and V vectors corresponding to all the words in our dictionary. So we'll sum over all possible center words. That's basically every word in our corpus. It's a huge number of words. And for each of those center words, we'll sum over all possible context words O. So if we're using a window of 5, we have 10 context words for every center word, except for the ones that occur at the ends of our phrases or sentences. And then for each of those pairs, we'll just maximize its log probability as given by the softmax model. And the parameters of this optimization now are the U and the V vectors. So that for every word, there are two vectors, a U vector and a V vector. Okay. Now, one thing that might immediately occur to you guys is that the number of vectors here is humongous, right? You might have a huge number of words, and for each one you have two vectors, and each of those vectors might be fairly high dimensional. It might have like hundreds of dimensions. So there are a huge number of optimization variables. But importantly, most optimization variables don't participate in most of the likelihoods. All right. So the U and V vectors for all possible words are our optimization variables. We sum over all possible C and O combinations, and we maximize their likelihood, the log likelihood, where the likelihood itself is given by the softmax expression. Okay? That's a simple way to get these U and V vectors, although it's computationally quite costly. Okay. So this is basically the idea behind Word2Vec, although the actual implementation of Word2Vec is a little bit different. But let me go through the simplified version, and then I'll describe the complete version. So our parameters for this optimization are just the V and U vectors for every word in the dictionary. So if you sort the words alphabetically, you have like V aardvark, VA, etc., all the way down to V zebra, and then you have U aardvark, UA, all the way down to U zebra. Now, why do you have two vectors instead of one vector? Well, it makes optimization a little easier. It actually makes it easier to optimize if the U and V don't have to be the same for the softmax. But at the end, if you want a single vector representation of a word, you just average its U and V vector. So the way that you're going to use this is you'll just average the U and V for a particular word, and that's now your new representation of the word that can replace the one-hot representation in some downstream application like sequence-to-sequence modeling. So this gives us a representation of words that we could actually use. But we're not quite done yet, because in practice, if you have a very large vocabulary, it's very difficult to train the model quite in this way because of the denominator, right? So the numerator is fine, but the denominator requires summing over all the words in your vocabulary, which is definitely possible. It's just very expensive. So another idea, which is a little bit more complex, but turns out to get rid of this problem, is to instead set this up as a binary classification problem. So instead of asking what is the probability that this word is a context word for C, as opposed to any other word, you could instead ask what's the probability that this word is right or wrong. It's basically a binary classification problem. True if this is a good word, false if it's not the context word. So the difference between these two questions is that P of O given C above has to assign a probability to every word in the dictionary that that word is a context word for C. Whereas this binary classification problem just takes in two words, an O and a C, and it just outputs true or false, a probability of true or false, if that O goes with that C. So you can think of it as that P of O is the right word given C. Now, O is the right word is a binary question. So you just need a binary classifier. And the way that we'll create this binary classifier is by using a sigmoid. So if you remember, if you think all the way back to the logistic regression lecture, we talked about how we need one vector for every class, except in the binary case, because in the binary case, there's a simplification we can do because we know that if you get the probability that something is true, the probability that it's false is just 1 minus that. So you really only need one vector. And in that case, the softmax function actually reduces to a sigmoid. So the sigmoid just has this shape. This is actually very reasonable now, because now we're just saying, take UO and VC, compute their dot product. If their dot product is large, then sigma of that dot product will be close to 1. If their dot product is a very negative number, then sigma of that will be close to 0. And if their dot product is some sort of medium, sigma of that will be somewhere in between. So this is the expression for sigma, for the sigmoid function. Okay, now the great thing is that this probability now depends only on UO and VC, and does not depend on the U vectors for any other words in the vocabulary, which means that you no longer need to sum over all these other possible words. But by itself, this is not good enough. So if I just take this P of O is the right word given C, and I replace that, I replace the P of O given C in the original objective with this thing, what's the bad thing that might happen? Imagine if all the U vectors and all the V vectors are exactly the same and gigantic, such that for any U vector and any V vector, their dot product is a very large positive number. Now, all of the P of O is the right word given C probabilities will all be very large. And that will actually maximize this objective. But of course, that's crazy. You don't just want to make all the words look similar. So the problem with using only this term is that it will push similar words close together, but it won't push different words apart. Essentially, it's like a classification problem where all your labels are the same. The labels are always true. In order to make this work, you also need to add in some examples of O's that are not the right word for C. So what we can do is we can also define P-O is the wrong word given C. And there are a variety of ways we can define it, but a very simple one is just use the negative of the dot product. Okay? And now what we'll do is for every center word C and for every context word O, we will add the log probability that O is right given C, and then we'll sample some other random words, just random words from the dictionary that are obviously not the same as O, and we'll add those as labeled with wrong. So we'll take the real O and C tuple and we'll label it as right, and we'll take some random words and label them as wrong. So now we have both true and false examples, and now if we actually train for these binary classification problems, we'll actually get something sensible. It is not the same as the original softmax, but it still works pretty well. Okay. So the negatives here are chosen randomly. The wrong words, we call them negatives, they're chosen randomly. Now, as a little caveat, it is possible that you would accidentally sample a negative that is actually not wrong. Like, maybe the context word is president and the center word is rule, and then you accidentally sample like W as king, right? King is actually a reasonable context word for rule, but it would be treated as wrong here. The reason that that's okay is because most of the time this wouldn't happen. So basically you'll see the word rule and king as a valid context center pair much more often than you will accidentally see it as the wrong pair. So that means that in general this will actually work, even though you might accidentally sometimes get an incorrect negative. Okay, so the summary of word2vec is that we're going to have this probability of right and a probability of wrong. So the positive dot product passed through a sigmoid is the probability of right, the negative dot product is the probability of wrong. For every center word, you take the correct context words O and you label them as right, and then you sample some random words and you label them as wrong, and then you train this whole thing with respect to the U vectors and the V vectors for every word. And of course, in reality, we would do this with stochastic gradient descent, which means that we would randomly sample a batch of sentences, we would randomly sample a batch of words in sentences, and for each of those words, we would randomly sample a context and we would randomly sample some negatives. And we'd have a batch of size, let's say 32 for every gradient step, which means that every gradient step would affect somewhere on the order of 32 vectors, 32 times 3, I guess. And of course, this P of right and P of wrong is just the sigmoid, so we can equivalently write it like this. So the intuition behind it is that this objective is going to push VC towards UO and away from other vectors UW. Okay, now if we train this kind of word2vec embedding, there are a few good things that it will do. Of course, it will put similar words close together, but in practice, it also sometimes gives us interesting kind of algebraic relationships. Since words are now embedded in Euclidean space, you could, for example, do something like take the representation for the word woman and subtract the representation for the word man. So that gives you a man-to-woman vector. It's a vector in the space that intuitively is the direction you go to turn a man into a woman. And then you could take that little vector and you can add it to some masculine word like uncle and get something that looks like the embedding for the word aunt. Right, so it's a kind of analogy. Now, the degree to which this actually works in reality is a little bit controversial. So sometimes this happens, sometimes it doesn't. So, kind of under idealized cases, you might get these algebraic relationships. In reality, you might not, because there's nothing guaranteeing the word2vec embedding to have linear relationships like this, right? So it'll have Euclidean proximity. Proximity is not the same as linearity. So sometimes you get these, sometimes you don't. So this is a little bit idealized. Most relationships are not nearly this nice, but it does, I think, make the point that there is, some semantic meaning in the geometry of the space that you get from this. Here are some examples of these sorts of analogies computed using word2vec from a 6 billion word corpus of news articles. So the way that these were done is they took the word in the second column for the word pair 1 and subtracted the word in the first column. So for the capital city, you take Greece and you subtract Athens. And then you add that to Oslo and you take its nearest neighbor, and its nearest neighbor is Norway. Okay, so Greece minus Athens is like is capital of vector. So you add it to Oslo. That's like saying, well, what is Oslo the capital of? And you get some vector. Now that vector by itself doesn't mean anything, but you find the word in the dictionary that has the nearest vector, and that will be Norway in this case. Similarly, you can do some other relationships like present participle. So thinking minus think, add that to read, and you get reading, or you get a vector whose nearest neighbor is reading. Similar principle. Here they took the right side of the relationship column, subtracted the left side, so Paris minus France, added to Italy, and you get Rome, and so on. So there's some reasonable structure going on here. All right. So a summary of word2vec. What do we do with all this? Well, you can use this vector representation of your word in place of one-hot vectors for whatever downstream model you want to train, like a seek-to-seek model or a transformer. much more meaningful for downstream applications than one-hot vectors because Euclidean proximity actually means something. And you can train word embeddings on large unlabeled data sets and then use as input into a supervised model that is trained on a much smaller amount of data. So you can think of this as a very simple type of unsupervised training.